Hello, my name is José Manuel, and I belong to the Physics Applied Department, the UPC, and I want to talk to you about the research line in which I'm doing my PhD, convective instabilities in rotating fluids. Rotating fluids are a topic of great interest in fluid dynamics nowadays because there are many industrial applications where they are involved. For example, those environmental cleaning procedures, such as cyclone dust collectors or vortex grid chambers, where a current of air or water are cleaned from impurities due to the action of rotation. They are also important in turbomachinery, where turbines or compressors present energy transfer between fluid and rotor, so it is important to know the dynamics of the fluid in order to improve the efficiency of these machines. However, the problem becomes even more interesting when we add a thermal gradient to the problem, because the competition between thermally driven motion and the background rotation leads to flow circulations which are similar to the large-scale flows on the Earth, such as atmospheric cyclone formation or the mesoscale eddies in oceans. And more recently, it has been pointed out the possibility for convective instabilities to be the responsible for turbulence in accretion disk. And this is actually the main motivation for my PhD. There are several ways to face these kind of problems, but what we do is to study those intermediate states which appear in between the laminar or regular flow and the completely disordered or turbulent flow. The Navier-Stokes equations give the velocity, the pressure, and the temperature for any point of the fluid if we are able of solving, because this is a complicated task. So what we do is a numerical approach of this set of equations. I want to show you an example of what we typically do. So here, I consider the fluid enclosed in a cylinder, which is rotating around its vertical axis, and subject to a vertical thermal gradient. So I mean, the bottom lip is hotter than the top lip. To the right, you see a bifurcation scenario corresponding to this system. The first thing we have to do in this kind of analysis is to calculate the basic or laminar flow. So here I show you the temperature corresponding to the basic flow to this system. It's very easy to describe in the lower picture what is happening here. The warm fluid at the bottom, which is lighter than the cold fluid, goes upward, and at the same time it is centrifugated towards the center of the cylinder, while the cold fluid goes to the outer part of the cylinder. In the upper picture, you see the asymmetric character of the solution. So, once we have this basic solution, we have to incorporate a small perturbation to this system and look for the values of the control parameters for which this state loses its stability. So, if we identify the solution here and we move the control parameters, we finally reach this curve for which this state becomes unstable and a new solution arises. This new solution is illustrated in these two pictures. Now you see how the asymmetric character of the previous solution is broken, and there are three branches of warm fluid appearing now. So this is what we call an intermediate state between the laminar flow and the completely turbulent flow, which will come for larger values of the control parameters. So this is basically what we do. So thank you very much.